In this lecture, we're going to look at the HR diagram through the lens of the physics that we've applied to understand how stars ought to be structured. And we're going to apply in particular these proportional relationships between things like luminosity, mass, and age. And we're going to show how the application of those simple formulas allows us to find other ways of measuring distances to stars and also the ages of stars. So a few weeks ago, we encountered the first way astronomers measure how far away stars are using measurements of their parallax. And that enables us to measure the distances to stars up to about 50 parsecs away, and that's about 10 to the 5 stars, 100,000 stars. Sounds like a lot, but that's a tiny, tiny fraction of the stars in our galaxy. And 50 parsecs is a tiny, tiny distance compared to the size of the galaxy. So how can we do better? So the next two methods of measuring the distances to stars take advantage of the patterns in the Hertzsprung-Russell diagram. So let's look at an example Hertzsprung-Russell diagram that you yourselves have plotted. So this is the HR diagram of the Pleiades cluster. This is luminosity versus surface temperature. And you'll have noticed that HR diagrams have the same characteristic pattern. Most of the stars, usually, in a particular star cluster, are arranged in this band that goes from top left, that's high luminosity, high temperature, down to bottom right, which is low luminosity, low temperature. Now remember our analogy with the mosquito trying to figure out the life cycle of humans. If you plot the mass and height of humans, then they all cluster around the average height of an adult. That's because most humans spend most of their lives at that average weight and height. Most of our lives are spent as an adult human. That accounts for a good 60–80% of our lives. So by the same logic, this band being where most of the stars cluster tells us that this is where most of the stars spend their lives. So all stars spend most of their life somewhere on this track here. And you'll have noticed that it has the same appearance no matter what star cluster we use. And that's because the laws of physics are the same everywhere. Stars are obeying the laws of physics, and it's the laws of physics that is responsible for this particular pattern, as we'll begin to discover. But what this tells you is that if a star is on the main sequence, then if you measure its temperature, then you can get its luminosity, and vice versa. And that's extremely useful, because one way to obtain the temperature of a star is by measuring its spectrum. If you can accurately measure the spectrum of a star, then you can measure its temperature. And if the star is a main sequence star, and most stars that we see are, because all stars spend most of their lives on the main sequence, then if you measure its temperature, then you immediately get its luminosity. And its luminosity gives you its absolute magnitude. We measure the brightness of the star, which gives us its apparent magnitude, and the difference between the two is the distance modulus, which gives us its distance. So this is a second way to measure the distance to stars. This technique is known as spectroscopic parallax. Spectroscopic because we start off by measuring accurately the spectrum of the star, the absorption lines present. It actually has nothing to do with parallax. So don't get confused with the term spectroscopic parallax. It has nothing to do with actual parallax. We can take accurate spectra of stars within our own galaxy, so out to a distance of about 10,000 parsecs. So that greatly increases the range which we can measure stars over, from 50 to 10,000 parsecs. And this is the second rung on the cosmic distance ladder. And we can check that we get the right answers here if we measure the distance using the spectroscopic parallax method to stars in clusters that are within 50 parsecs, because then we can actually measure the distance in two different ways. And if they agree with each other within the accuracy of the observations, then we know we're on pretty safe ground. Okay, let's examine a second way of measuring the distance to stars by comparing the HR diagrams of different clusters. So we'll take the Pleiades and the Hyades as examples. We've already seen the Pleiades HR diagram with its main sequence, the band down the middle of the diagram here. Our sun, remember, has a luminosity of 1 times the luminosity of the sun and a surface temperature of about 5,500 degrees Kelvin. So that will put it here on the main sequence. The Hyades is 46 parsecs away. So the Hyades star cluster, we can actually still measure the distance to using ordinary parallax, which means that we can convert apparent to absolute magnitude and obtain the luminosity of all the stars in the cluster. So its HR diagram looks a little like this. Now suppose we didn't know the distance to the Pleiades, but we did know the distance to the Hyades. Okay, so the blue points here are the Hyades absolute magnitude, which we can plot because we know the distance to the Hyades, and the red points here are the Pleiades apparent magnitude, assuming we do not know the distance to the Pleiades. Now take a look at this. Notice that the main sequences on both clusters are parallel to each other. They have the same shape, and that's because the appearance of the main sequence is driven by physics. And physics is the same no matter where you are in the universe. But this is really useful. Let's think about it. We don't know what the absolute magnitude is of the Pleiades, but we do know that all main sequences appear along this same line of absolute magnitude versus the color of the star. So we know that if we did know the absolute magnitude of all the stars in the Pleiades and we plotted them, they would all appear on this black line here, just like the Hyades does, because physics is the same everywhere. So we actually do know the absolute magnitude of these stars. All we have to do is take the main sequence of the Pleiades and shift it vertically upwards until it overlays the main sequence of the Hyades, which we do know the absolute magnitude of. Well, the difference between the main sequence of the Pleiades and the main sequence of the cluster that we know the distance to is just the difference between the absolute and apparent magnitude of the Pleiades stars. This is the distance modulus. So we know what the distance modulus is for the Pleiades, therefore we can calculate the distance to the Pleiades. So let me just reiterate. We don't know the distance to the Pleiades, but we know the apparent magnitude here. But we know that if we did know the absolute magnitude, the Pleiades would be shifted up to this line here. So we know what the difference between the absolute and apparent magnitudes is of the Pleiades, and that allows us to find the distance using the distance modulus formula. So this is called main sequence fitting, matching the main sequence of the HR diagram of a cluster you don't know the distance to a main sequence of a reference cluster such as the Hyades that we do know the distance to. And this allows us to measure the distance to star clusters so long as we can measure the individual brightnesses of those stars, which we can so long as they're within our own galaxy, so out to about 10,000 parsecs. So this gives us a third way of measuring the distances to stars. And again, we can measure the distances using two different methods and check whether they agree just to make sure we're getting things right. And it turns out we are. So using these methods, we can measure the distances to all visible stars in our galaxy, which means we can measure the size of our own galaxy, which is great. Okay, one final thing that the main sequence tells us. Let's think about the scaling relationships again. So luminosity is proportional to mass to the power of alpha, and the main sequence timescale is proportional to mass to the 1 minus alpha. So this first formula tells us that the higher the luminosity, the more massive the star is. So at the top end of the main sequence up here, that's the high luminosity end, that's where the highest mass stars are. But this formula on the right tells us that the highest mass stars have the shortest lifetimes on the main sequence. So they will end their main sequence lives first, and when they end their main sequence lives, they will disappear from the main sequence. They will move elsewhere. We'll discover where they go on the HR diagram later. But the point is that if we were able to measure the HR diagram of a cluster over, say, 10 billion years, and we were able to live that long, then what we would see is that the main sequence would start off going up to high luminosities. Then, as time went on, those high luminosity stars would end their lives on the main sequence first and vanish. So the main sequence would start getting shorter and we would start losing stars at the high luminosity end. So it would get shorter and shorter with the high luminosity end moving down and to the right, and the low luminosity end wouldn't go anywhere. But we can't watch a star cluster for 10 billion years, but what we can do is look at what it looks like now. So this is the Pleiades cluster, and we can say, oh look, the main sequence stops here at a luminosity of around 1,000 times the luminosity of the Sun. That means that all stars with a higher luminosity have ended their lives. Well, that tells us what the age of the cluster is. If the cluster is old enough that we're at the point that 1,000 luminosity stars are just beginning to evolve off of the main sequence, then we can rearrange this formula, assuming that these stars are within the mass range where alpha is about equal to 4, which they are, and we find that the mass of the stars up here that are just about to evolve off of the main sequence is around 5.5 solar masses. Plugging that into the age formula, apologies, this should read 5.5 to the power of -3. This is just the mass here that we found here inserted into this formula here. Gives us the age of the stars that are just about to evolve off the main sequence. They're about 6 times 10 to the 7 years old. That's 60 million years old. Well, all the stars in the cluster were born at the same time, so that tells us the age of the whole star cluster. The Pleiades is roughly 60 million years old. So the end point of the main sequence, which is known as the main sequence turnoff, tells us the age of the star cluster. If we look at a globular cluster, a much larger cluster of stars, and look at the HR diagram of that, this is an example HR diagram of M5, a very large globular cluster, you see it has quite a different appearance. The main sequence is very short indeed. Okay, this is the main sequence line here, and we've only got the low luminosity, low temperature end remaining. All of these stars up here have evolved off of the main sequence and are now doing something else, something that we'll talk about in a week or two's time. So the main sequence turnoff is around here, and we can use that to calculate the age of the cluster in the same way. So if we compare the HR diagrams of different clusters, we see that they all have different main sequence turnoffs and therefore different ages. Some of them indeed, like M41 and M11, no longer have a main sequence at all. So you see that the application of just a little simple physics allows us to do an awful lot, to figure out an awful lot about the properties of stars and the ages of stars.